Welcome back. Introduction to exponential functions. If you're going to be studying functions at some point, I hope that you will study exponential functions because they're extremely useful in applications as you go through sciences, depending on which programs you end up in the future. So the video is intended for students who are studying functions in some particular way. So some things that I'll talk about, hopefully will ring a bell. But if you're also watching this just out of kind of introduction purposes or curiosity, hopefully you're going to be able to understand it. My main setup here that you see in terms of functions and even relations, I love grasping and taking the input, which is your independent variable, and then your output, which is your dependent variable, and then trying to see that you have this box inside and something happens to our inputs. Now these inputs that we have in this case are going to be taken by our actual box, and it's going to be a function which is going to be exponential. And exponentials, when you're just studying in terms of introductory purposes, they will look kind of like this. So you will have a function, so let's say f of x is equal to, and it will be sum a multiplied by b and raised to the exponent x. This is something new because of the fact that now you're taking your input and it is appearing in an exponent. It never used to appear in an exponent. If you're going to be studying linear functions, so y is equal to mx plus b, if you're going to be studying quadratic functions or polynomial functions, or any functions pretty much up to this point, our input never really existed as an exponent, but now it does. And because it is an exponent, that's why we call this an exponential function. And it is the simplest of exponential functions that we have. And that's what I'm going to talk about in this video. Okay, so I just want to introduce you to this concept. So there's something you may wonder about this a and b. Our a is basically some real number. So this a that we have, so maybe I should formally state it, so it is an element of real numbers. Now we will assume that a is not equal to 0 because we don't want to zero this function off, because then 0 times b to the power of x would have been 0. So that's a. So it could be positive, it could be negative, it can be any numbers. Okay, so that's what a typically is in this exponential function. Now our b that we have, so that is our base. So our b is going to be our base. When you study exponents, you should know kind of what the base is. And in terms of reviewing exponents in general, if you like, you can go back to my grade 9 material, or I'll put up a link maybe up above there. You can watch the playlist just to review the concepts of exponents. So if b is your base, are we going to restrict this particular base? Yes, we will be restricting it. Now we're going to restrict it into kind of two different categories. We're going to restrict our base so that it is either less than 1 or greater than 0. And then the other restriction might be, so it can also live, that it is actually greater than 1, okay, in some particular way. So maybe, I'll write it in this way where b is greater than 1. So it's bigger than 1 in some way. So what do we want to be able to do with these exponential functions, and how do we want to get some intuition into them like we would with, let's say, lines or quadratics, or they're parabolas or polynomials or any of those kind of functions? Let's start off with making it simple, and we'll take some examples and I'll show you how I want to break this down in terms of table of values. So I want to break this down and show you some intuition into these exponential functions. So first, let's grasp and just kind of plot a table of values for maybe some specific cases. And what I'm going to do first is, then I'm going to assume that this a is equal to 1. Okay, so in this particular video, I'll just make it simple and just say, let's fix a is equal to 1. So what does that do? Well, what that does for us is that it kind of removes this a, because if a is equal to 1, okay, then our function is even simpler, and it's just simply the exponential itself, where you have a base raised to some exponents, which I think is definitely worthwhile studying. It's kind of like your parent function that you have, and we did study some parent functions kind of in grade 11. So maybe I'll put up a link up above there for parent functions if you wanted to review. This will be our parent function for exponentials, and then we can do transformations and so on to it later on. So if we're going to make this assumption of a is equal to 1, then what do we want to be able to find out for these cases? Well, we want to talk about its domain and range, what that could be. We want to talk about intercepts, are there any, and kind of zeros, if you were thinking of quadratic or polynomial functions, do those exist? And then asymptotes, and in this case, we will have some asymptotes for particular cases. So let's take an example where I'm going to take this entire input and output relationship. So I'm going to copy this down, and I'm going to fix my b, so we'll make it specific kind of for two cases. What I'm going to do is, because I want to create a table of values, so let's fix b. So I'm going to let b, be equal to, let's say 2. And then what I'm also going to do is, because there's kind of two different cases that you'll see, and once you understand those two different cases, it's much easier to extrapolate to any base that you would like. So notice that b is equal to 2 basically falls in this region right here, where it is, so I apologize, right here, falls for b is greater than 1. And then we want to also get one case in here, which is where b is between 0 and 1. So I'm going to make b, let's say 1 over 2, or simply 0.5. So we're going to take those two cases. So we either have, if I would be writing it as the function itself, so this would have been 2 to the x, or if I changed it, maybe I'll call it g, so that I can rename them. And this is, let's say, 1/2, to the x, or you can put 0.5 to the x, so it would mean exactly the same thing. So what would this give us as a table of values? So I'm going to create a table of values for us here for both cases. For, let's say, some integer inputs, and then we're going to see and try to see how that would look like. We're going to try to see a particular pattern that might emerge. So let me do that in fast forward fashion. All right, so welcome back. So here are a table of values for the two cases. So I have 2 to the x, and then I have 1/2 to the x. So because my inputs now are basically exponents, and this is why it's kind of useful to understand exponents and then how to simplify them. So I took values from -3 all the way down to 3, substituted them in, and then got my results, and then my results are right here. So notice if you have -3 as your input, because it acts as an exponent, all of a sudden your answer is, or your function provides you 2 to the -3, which really is just 1 over 2 to the 3, because it's a negative exponent. And then 2 to the 3 is 8, so the result is 1 over 8. Now you can change that to decimal if you like, but I think if you're comfortable with exponents, then that answer should be fine. And now 1 over 8 is going to be rather small. Now if you have -2, you repeat the process and you'll get 1 over 4, then you'll get 1 over 2, then you'll get 2 to the 0, which is 1. And then now all of a sudden you get the exponents which are positive. So you get 2 to the 1, 2 to the 2, 2 to the 3, and the number starts to grow. So now if we kept going in the negative direction or in the positive direction, you'll notice that if we go in the negative direction, our answer, okay, let's say if we had negative 100, it would have been 2 to the negative 100. And that would still provide us a positive result, but it would have been very small. So it's interesting what happens here, that if you have 2 to the x, then our actual result, so kind of was going to start looking, if we were plotting it on the x and y axes, all the answers are positive. And what you would have is they would slowly, so as you would plot them from, let's say if it was negative 3 right here, negative 2, negative 1, and then here 1, 2, and 3, you know, and if I plotted these points, so this would have been rather small, and then it slowly tries to take off right here, and then it goes through 1, and it goes to 2, and then all of a sudden it starts to slowly kind of skyrocket because the exponent, so if we kept going, this would have really just exploded exponentially upwards like this. And here in this direction, it would have been going more and more towards 0, because negative inputs, if you raise them, okay, if 2 to a negative input and then you just make it bigger and bigger and bigger, it's going to make that number smaller and smaller and smaller and smaller, but still always positive. Now, if we did this, okay, when b is between 0 and 1, so if in this case I took 1 over 2, now notice that, this kind of reverses the process. So I had 1 over 8 when the input was negative 3, but here all of a sudden I have an 8. Okay, here I had 1 over 4, and here I have a 4. 1 over 2, here I have a 2. So it's like it's going in reverse. So instead of skyrocketing upwards like this, okay, when it's b is actually 2, or which is greater than 1, and that's going to be true, and I'm going to just show you on Desmos once I start plotting it. Here it kind of looks like it's going in reverse. So what I'm going to do is I'm going to kind of copy this down, okay, and so I'm going to duplicate it, bring it down in here. And if you were trying to plot this table of values, then what would have been happening, okay, is that this would have been going like this. So it's almost like it's a mirror image, okay, which is just going in the opposite direction. So that's what would have happened right here with that exponential. Now, this brings about a few things, but, okay, I'm going to take out Desmos so that we can see this directly. So if I take out Desmos, I'm going to say, so f of x, I'm going to make f of x, okay, equal to, so notice it's b, okay, raised to the x. I'm going to put up a slider in here for that, and I just want to show you what happens in these instances. So now let's take a look and see what happens when we do go between 0 and 1. So within here, okay, so I'm going to, maybe I'll change it. So let's first concentrate just between 0 and 1. So if I go in here, notice that indeed my plot, okay, on the negative inputs, okay, it looks like it's skyrocketing upwards because it's getting bigger and bigger and bigger. All right. And so the closer you get to 0, okay, then you're skyrocketing and you're getting closer and closer yourself to the y-axis. All right, so notice it's 0.05 as your b. And as I keep moving this away, okay, it moves away from the y-axis, okay, and goes kind of further and further and further. Now, one thing you should note is that we are always stuck at an intercept of 0, 1. Why? Because if your input is 0 and it acts as an exponent, any number, so any b, any base that you take and you raise it to the 0, what do we know about that? The answer is always 1. So it doesn't matter what we do here, it will never change that intercept for us in terms of the y-intercept. Okay, but as we get further and further out, okay, and closer to 1, okay, it's going to start looking more and more and more. It kind of flattens out. right? Still exponentially goes up, but it slowly starts to flatten out. Now, what happens at 1? If you put it at 1, if the base is 1, it doesn't matter what the exponent is. We know that the result is always 1. So it creates a flat line for us. So we would have just a flat line going straight through 1. But anything else in between, okay, all of a sudden it starts to look like an exponential, but it blows up this way. So this is really neat to be able to see that. All right, so that's the first one that we have. Now, ours was 0.5. So let's get to 0.5 here, or at least as close as I can. There we go. So that's how it would look like. That's my 0.5. Now, okay, and so within here, let's call this g of x, because that's what I put right here. I called it g of x in here. All right, so when it is between, let's say, 0 and 1, I'll call it g of x. And when it is more than 1, let's see what happens in that instance. And that I'll call that f of x. So here I'll have f of x. Now, I've already used b, and I want to keep this b in here. So maybe what I'll use, instead of using b, it's still b, okay, in that case. But I want to call it something different. Let's maybe call, let's call it d, okay, and raise it to the x. And then I'll put a slider, and I want this between 1, okay, or any number above 1. Let's go as far as 20. I think you'll get the point. I mean, it will work for anything else. So let me zero off what we had, okay, when it was between 0 and 1. Now, what happens when it is kind of, we already know what happens at 1, right? It's a flat line, as you can see now on the screen. But now what's going to happen when it's more than 1? Okay, so what is going to happen? So now as I kind of move along, okay, what you notice is now it's going in this direction. And as I get bigger and bigger, meaning here as my base gets bigger and bigger, okay, the exponential just blows up much faster and it gets closer and closer to the y-axis. So for us, we had kind of b is equal to 2, so I'll put it at 2 right there, and then I'll bring that. And you notice that it's a mirror image in the y. Okay, so if the base was 0.5, which is 1 over 2, okay, or if the base is 2, they're just mirror images of each other. Okay, so that's what you would have. So if I would put, for instance, okay, so within here, so let's say I would put, 0.25. Let's see if I can get to 2 pi. There we go. 0.25 is 1 over 4. 1 over 4. So that means if I make the base 4, so here, if I move this to 4, like so, okay, so notice again, looks like I have a mirror image. So you should get some kind of understanding when you're looking at these graphs and what happens between these exponentials. They're actually not as difficult to comprehend, especially the base, okay, kind of the parent function of this exponential, which is just b to the x. Okay, so let's come back now because we talked about these cases, right? So we talked about the case when our base is greater than 1. So we saw that the exponentials in this case kind of go and look like this, and then they just explode on us. And then here they just start to approach and then get closer and closer to 0. We'll talk about that maybe in the domain as well. The second case that we had was when our base is between 0 and 1. And in this case, it kind of did the reverse, right? So it was, I guess I'll try to fit it in here. So it kind of went like this, where it starts to approach 0, okay, and it gets closer and closer to 0, and it explodes on the negative side. But now we have these two interesting cases, which most of the time actually in school, I believe they're kind of ignored. But they're definitely interesting, and we should be able to understand them in some way. So the first case is, what happens, if the base is equal to 0? I mean, it's not a very interesting case. but it does force you to try to understand exponents a little bit. Now, if you take this case, so if you have this, I'm going to just write this. So what that would mean is we would have our function, so let's say f of x would be equal to, so our base is 0, and then it is raised to the exponent of x. And nothing really happens when x is positive. So if x is positive, so from 0 onwards, then basically it's just 0, because if you take 0 and you take it to the positive exponent, so what will happen in that case is you're going to get, let's say, 0 to the 1 or 0 to the 2 or 0 to the 3.5. It doesn't matter, it's still going to be 0. So that's what happens in this particular case. Now 0 to the 0 is kind of funny, and so if you're thinking about that 0 to the 0, if you forgot about 0 exponents, I'll actually maybe put up a link up above there. You can kind of refresh yourselves. I think I put it in the grade 9 video. So 0 to the 0 is interesting, certainly, but on the positive side, nothing interesting happens. Now, if your input is negative, that actually creates quite a bit of a problem for us, because, so let's say, imagine, I'll just take it a simple case. You can take it to anything, but 0 to the negative 1, well, what this means is, this means 1 over 0 to the 1, right? And 0 to the 1 is just 0, which means you have undefined. And what you will find for this case, that when your base is equal to 0, and I'm going to actually, let me bring back Desmos here, and let's put this back into 0. All right. So what you will notice that your graph is actually on the positive side, 0, but it's not on the negative side. Okay. So that's what happens there. Okay. So here it's all zeros, okay, as you're going across, but it's not on the negative side. And that is because if you take and you have negative exponents, that 0 starts to appear in the denominator, and we get undefined results. Now, what about if you have the case when b is equal to 1? So that's this case. Again, it's not super interesting, but we should kind of know what that means. So what this would say is that you have a function, so f of x is equal 1 to the x. Well, in this case, it actually doesn't matter, because any input that you have, so for any x, 1 raised to some exponent is always going to actually equal to 1. So this becomes just a flat line, and you saw that actually in the graphs already, but let's put that in here. So you'll see just a flat line, so just flat lines like that. So those are the two interesting cases, and I wonder if schools teach it, but if they don't teach it, you saw it here, and you kind of should have some intuition into that. The other part to which you might wonder, and you can certainly, that's a great question, I would love to get that from students, is, well, what about base being negative? Can you have a base which is negative as a function? So what if you had something like this? It doesn't matter what negative, let's say negative 2. All right, raised to the x. How does this look like? Does it exist, right, in some particular case? And that I will actually leave for you to think about. Notice we don't have it here, so something must go wrong. And think about what goes wrong. Why isn't this an actual function, right? So what is happening, okay? And you can think about some of the inputs, okay, that you might have. And just a hint, don't think only about integer inputs. Also think about, an input, for instance, like something like a half, or something like 1.6 or something of that nature, and you can try to calculate these things, and you're going to see that something interesting happens, because if your base is negative, there's a problem. All right. Now, if you won't be able to figure it out, you can put it down in the comments, and if I get a few comments, then maybe I'll make a separate little video on that as well. Okay, so now the last item that I want to talk about in this video is with regards to these domain and ranges for the cases that we had. And we'll talk about, and we'll assume, that we are referring to these cases. Okay, so for this one and for this one we just talked about, so you can think about that. So the domain for those two cases, it turns out that our input can really be anything. Okay, so our input for when b is greater than 1 or when b is between 0 and 1, so our domain within here is any input will work. And we saw that in our graphs, okay, so that any input actually works. Now the range is a little bit trickier because the range, I'll stick the range as y. So it can be any real number. However, in all our cases that we had, you've noticed that it is actually greater than 0. And even if you have, so if I go back in here, let's put it arbitrarily, let's say this is 7.9. Now it doesn't matter what b actually will be as long as it's between 0 and 1 or greater than 1. In both of those cases, we know that it skyrockets upwards. But very often, if you're going to draw it on Desmos, actually if you go in here, let's make it, whoops, okay. So if I go in here, notice that your value of y, is getting smaller and smaller and smaller. Now, eventually Desmos is going to put this at 0. Like notice it's 0. Don't get fooled. It actually never touches 0. It never touches 0. It doesn't matter how big, okay, in terms of big magnitude on the negative side your input is, it will never be 0. And now, why is that the case? Well, so let's imagine. So, we have, so our function, if you have b to the x. Now, if your b is some positive number, so let's, we had 7.9. Now, it doesn't really matter what it was, but on the graph that I just showed you. Now, if you have a negative input, even if it's a negative 100, don't forget what this means. This means 1 over 7 to the 9, okay, raised to the 100. So if you do that and you try to compute this, even on your calculators, it might show you that it's, 0. But technically, it's not really 0. It's going to be very, very small because it's 1 divided by an enormous number, but it never is actually 0. So if you make this input right here, bigger and bigger and bigger, it just gets closer and closer to 0. That's why your range is actually never 0. It's always above 0, and it just skyrockets up. And it doesn't matter if it's b bit greater than 1 or if your base is between 0 and 1. Okay, so in both situations, that's what your range will be. Now your intercepts, okay, are there any intercepts or any zeros? Well, our range is always greater than 0. So we actually don't have an x-intercept. So that's one thing. So there's actually no zeros to this, at least for this parent function when it's b to the x. Now, any other intercepts, well, we did see that every single graph that we had, it intercepts the y-axis at 1. So that we have seen, okay, in our pictures, okay, or sorry, in our graphs right here. That's the only intercept that it has. And again, that will not matter, so like I can make this whatever, okay, it's always crossing through 1. So no matter what the b will be, okay, for the ones that we chose. So that's your intercepts. And then lastly, the asymptote. Asymptotes, recall, are basically lines that our functions approach to eventually. They start to approach these, okay, as x gets very big or x becomes very big negative. So what happens? So these asymptotes that we have, maybe I'll put up a link to asymptotes up above to refresh you if you wanted a refresher on that. But for us, the only asymptote that we have in here is because our functions are approaching 0, okay, so in this case it's approaching 0 in this way. So our asymptote is actually the line y is equal to 0. And that is the case here. And if I flip it, okay, so notice that it goes this way, then in this case, again, y is still 0, but it just approaches in that direction. So those are actually your asymptotes. So we only have one asymptote here, and that asymptote is y is equal to 0. It's that flat line with slope 0, okay, and crosses the y-intercept at 0. And that finishes it, okay, for us. And that's the introduction to exponential functions, at least to the parent functions. And hopefully we'll see you in future videos. Okay, cheers everybody. Bye.